Alright team, it's time to put theory into action. We will simulate the impact of the vessel on a fender, considering mass, velocity, stiffness and damping. What parameters do we need to input? What parameters do we need to input? Mass, initial velocity, stiffness and damping coefficient, and initial displacement as 0. What about time step? How do we decide? So we need to decide over the time step also. What about time step? How do we decide it? How do we decide it? Small enough to capture the impact dynamics. So the time step should be small enough to capture the impact dynamics. It should be time step should be small enough to capture the impact dynamics. Let's start with 0.01 seconds. Start with 0.01 seconds. What's the equation we will solve numerically? This is going to be the equation we solve numerically. This is the equation we solve numerically. The classic spring mass damper. This is a spring mass damper system. X is displacement. Initial conditions at time equal 0, x equal 0. Velocity is negative v naught. Why? Since the vessel moves towards the fender. Since the vessel moves towards fender, we are saying that it's negative. Why negative velocity? Because the displacement will be positive in the direction of fender compression. Because the displacement will be positive in the direction of the fender compression. That's displacement will be positive in the direction of fender compression. Okay. I set the mass as 800,000 kg and velocity 0.25 seconds and stiffness value damping. Sounds good. What numerical methods shall we use? Iris method, Ranki quota for better accuracy. It is step through time, compute acceleration, velocity, displacement. At 0.002 second, displacement is this much and force is this much. Force rising fast. What's peak force? We need to see the peak force. Force rising fast. What's the peak force? Time versus force we have to see. Force rising fast. So what's the peak force we have to see? Looks like 900,000 that t equal to 0.15 seconds. How does that compare with our static calculation? How does that compare with our static particulars? We estimated 894,000 pound for 0.04447 deflection. How does that compare to the static? Compare with? How does that compare with? We have to ask how does that compare with our static calculation? Dynamic simulation confirms static analysis but adds time dimension. What about the damping effects? If we try changing C value and rerun, peak force drop to 600,000. By changing the damping, the peak force drop to 600,000 only. A displacement increased 0.5 meter. More damping lowers peak force but increases deflection. So more for damping, it lowers the peak force but increases deflection. Can we plot force versus time? So we can visualize it. Force spikes quickly, then tapers off. It seems like force spikes quickly and then tapers off. Displacement rises to a maximum and then rebounds slightly. So what does this teach us? What does this teach us about real world fender design? So what does this teach us about the real world fender design? Static energy gives a baseline, but dynamics is the key for safety margins. So static energy gives a baseline, but dynamic energy is the key for safety margins. We must consider peak forces, deflections, and duration to protect structures. So we need to do the dynamic analysis because the peak force could be more compared to the static, but static analysis gives a baseline, but dynamic analysis gives dynamic simulation is the key for safety margin. So we must consider the peak forces, deflections, and duration to protect structures. Let's dive into the physics. We model the vessel impacting the fender as a mass spring system. Who can write the governing equation? This is the governing equation. Initial conditions also we know. Now this is a second order linear differential equation. What is the characteristic equation? We know. We can find out the roots of the system. What do the roots look like? This is a root. So we can get whether it's over-damped system or critically damped or under-damped. Which case is typical for fender impact? That's going to be the under-damped, because fenders have elasticity, some damping, but not too much. So fenders have some damping, but not too much. It's elastic also. So let's write the equation for the under-damped case. So we know under-damped case. So how do we find the constants using initial conditions? So displacement also we can get it. Then velocity acceleration can be found by differentiating the displacement. So energy. So now let's consider energy. Initially vessel has kinetic energy. Now let's consider energy. Initially the vessel has kinetic energy, right? And the energy is transformed into strain energy. This half kx time and dissipated energy due to the damping, countless heat, and remaining kinetic energy that which decreases as versus loss. How do we verify the energy conservation? How do we verify the energy conservation? We know by ensuring this it's remaining the kinetic energy. This is the remaining kinetic energy, right? This is the dissipated energy. This is the strain energy. Can we calculate the maximum force on the fender? Can we calculate the maximum force on the fender? Yes, of course we can calculate. Peak force typically occurs before maximum deflection. What about the impact duration? It relates to the time for displacement velocity to return to zero to near zero. Approximate time duration is 2 pi by omega d. 2 pi by undamped frequency. How do you use the damping ratio in the design? Damping reduces peak force and oscillations. Damping reduces peak force and oscillations as well. Can we estimate the maximum deflection? Yes, we can get it. Let's see one sample problem. Vessel mass, initial velocity, and fender stiffness and damping coefficient. We can calculate the natural frequency. We have the damping ratio. Then we can get the damped natural frequency. Maximum displacement, we know. V naught by omega d into e power minus omega t into sine omega d. Calculate the initial factors. Then x of t is this value. Calculate the maximum deflection. Once we know the maximum deflection, we can see 0.4626. Calculate the maximum force. Maximum displacement is stiffness. Impact duration 12.5 seconds. Calculate the initial kinetic energy. Initial velocity. Using that, we can get the initial kinetic energy. So natural frequency, damping ratio, damped natural frequency, maximum deflection, maximum force, impact duration, initial kinetic energy, all we can get it. So what does this tell us? What does this tell us? The fender deflects nearly half a meter under impact. Nearly half a meter. It deflects nearly half a meter under impact. The maximum force is about 925 kilonewton, which the problem must withstand. And impact duration is around 12.5 seconds. Impact duration is around 12.5 seconds. So the force is applied relatively slowly thanks to damping. And how does the damping ratio affect this? Increasing the C increases damping ratio, reducing oscillations, peak forces reduces, but increasing the deflection time. This is the balance we manage in the fender design.